All right, let's jump into DeWitt's chapter 27, which walks you through the most common interpretations of quantum theory. This is one of those where I really wish we were meeting in person so I could watch you try to wrap your heads around this and sort of stop and explain stuff and see whether that unfurrows your brow. Since we have to do this virtually, let's make the best of it. Let's start with a kind of big picture characterization. Oh, and by the way, I'm going to try to do this in 2 lectures. It might take 3. I'll try to keep an eye on the time and see. A physicist compares quantum mechanics to a mechanic who is the most amazing mechanic you've ever seen at fixing your car. This mechanic can tell you everything about when your car is going to run out of gas, what kind of problems it will face under what conditions, but cannot tell you anything or much of anything about any of the parts of your car. That is a decent approximation of the situation in quantum theory. We can do unbelievable jobs of predicting what's going to happen, and then you try to break it down and understand the components out of which this whole arises, and as you're going to see in some detail, it makes your head start to hurt. I am not recommending that we alter how physics is taught, but from a purely logical point of view, in terms of what depends on what, rather than in terms of having to learn the math, for instance, it would make sense to start with quantum mechanics, because it is a mistake to think that quantum mechanics is Newtonian or classical mechanics with some extra bells and whistles thrown in. Really what's going on is Newtonian mechanics is an approximation of quantum mechanics. So quantum rebuilds everything from the ground up. Classical mechanics just gives you a rough guide for things that aren't too small or moving too quickly. The situation is pretty similar in relativity. Newtonian mechanics gives you a pretty good approximation for objects that are not moving too quickly relative to one another or are not subject to large effects from gravity. Okay, those preliminaries out of the way, let's jump in. The standard view, Copenhagen views, is another characterization of this family of views. Of the mathematics, Schrodinger's math is the main stuff, and that's a wave math. Heisenberg has a system, quasi-particle math going on. If you were to give a physical interpretation to the math, it looks like there is wave activity. The photon or electron is a wave traveling both towards the slit on the right and toward the slit on the left. And that works if you leave the setup alone and you get the alternating lines on the photographic paper. But if you put a detector in place and turn it on, you only measure activity at one of the 2 slits. So if there was a superposition, which is to say, activity or stuff at both the slit on the right and at the left, how is it that instantaneously it disappeared from one place? So what happened to the other energy or stuff, and what is it about the measurement that produces that? Those are the questions that standard or Copenhagen views invite. DeWitt uses the terms objective and subjective excessively loosely, in my view. What he really seems to have in mind is something like interest relativity. He compares a thermometer sitting in your backyard to a chair sitting in your backyard. From a certain standpoint that he calls objective, both of them respond to changes in temperature. But it's not a subjective matter that thermometers are better at measuring changes in temperature than chairs are. It's relative to our interests, but just as if you're interested in cutting things, a sharp knife is objectively better than a dull knife. If you're interested in measuring things, a thermometer is objectively better than a chair. So I'm not happy with DeWitt's way of putting it. I invite you to consider banning the words objective and subjective from your vocabulary until you commit enough philosophy to get reasonably clear about them. As you can see, professional philosophers are not always as clear as they should be about them. But DeWitt's main point is that measurements don't constitute any kind of natural grouping. We don't have a theory about anything physical that distinguishes measurement context from non-measurement context, measurement devices from non-measurement devices. We cannot go any deeper and say these are the sorts of things that a system will count as performing a measurement operation, whereas other physical processes won't. We have no answer to that question, that demarcation between measurement context and non-measurement context. One thing I like about DeWitt's way of putting it is the failure of universality. One of the great achievements of Newton's Principia was using the same three laws of motion and principle of universal gravitation to cover motion in the heavens, motion between the moon and the earth, the tides, ballistics, projectiles, all that sort of stuff. We like it when we can do the mostest with the leastest. Quantum theory looks like it's backtracking from the standpoint of universality. The math is fundamentally different in a measurement context than it is in a non-measurement context. We do not have a broader category of math that will apply to both contexts. And so rather than making the kind of progress that we saw as Newton is able to use the same laws to cover more and more phenomena, here, as we try to cover the phenomena, we have to divide things in a way that we don't have a principled account for handling. All right, one thing to keep in mind is you cannot observe a superposition. All this stuff about interpretations of quantum concerns what's going on when we're not observing. The observations themselves were covered in chapter 26. Those are the quantum facts. But if you try to observe the superposition, you collapse it. This is called the collapse of the wave function. Mathematically, you add this thing called the projection postulate to the Schrodinger math. We're not going to worry about the Heisenberg math. Basically, you stop the wave math from evolving the way it would if there were no measurement going on, plug in the result of the measurement, and then restart the wave math. So it's disappointingly arbitrary in a certain sense. You just have to tell the system what happened when you made the observation. You can't predict the observation. You can only predict a probability for the observation. Then you plug in what you get and you start the math over again. So you don't derive your observation from the math, you add your observation to the math. It might be easier to look at a slightly simpler quantum phenomenon. Radioactive decay on a standard interpretation of quantum mechanics is irreducibly probabilistic. A given atom of, say, uranium just has a brute probability of decaying within a certain time frame. Let's say the probability is 0.6. And then you have two atoms that are, so far as you can tell, identical. One of them decays in that time frame, the other doesn't. The explanation is just, well, sometimes things that are probable happen and sometimes things that are improbable happen. We can't get a deterministic explanation. Back to Hume in some ways, there's nothing that makes it the case that one of the atoms was going to decay and the other wasn't. It's probabilities all the way down. This is one of the things that drove Einstein a little crazy about the standard interpretation, leads to his famous quote, "God does not play dice." On the standard interpretation, the laws of physics are fundamentally probabilistic rather than deterministic. All right, we'll wrap this mini lecture up after a discussion of Schrodinger's cat. This is another in our line of thought experiments. We saw some from Galileo, for instance, designed to convince us that some experiment that we cannot perform would have a particular result. It is a setup for getting macro level, big observational states of affairs, what the philosopher John Austin calls middle-sized dry goods, lions and tigers and tables and chairs, that kind of stuff. We want to try to get implications at the level of everyday objects from quantum phenomena. So the idea is you set up a double slit experiment or a half-silvered mirror experiment. If the particle is detected at one of the detectors, the cat will die. If at the other, nothing will happen. So don't get too upset about this. It's a cat, not a dog. This would be terrible if it were happening to a dog. Clearly, I'm a dog person. So Schrodinger's idea, and Bohr sort of talked him out of this realist construal, got him back into the Copenhagen fold. But Schrodinger's initial idea is to try to bring out our realist impulses here. it seems very troubling to say prior to the detector going off, the cat is in a superposition of alive and dead states. Notice that could be true for all we can observe because a superposition is not the sort of thing that we're able to observe. So Schrodinger's just trying to show you the weirdness involved in standard interpretations. If you take the math seriously, give it the physical interpretation that it most readily calls out for, then you're going to say there's a superposition of activity at both slits, one of which instantaneously and suddenly disappears for no reason that anybody can give. And then you get the outcome that you can observe, which is activity at one of the two slits. That is a possible reading of the phenomenon. It's just very strange at the macro level because it commits you to this idea that prior to the detector going off, the actual cat was in a superposition of live cat and dead cat states. So that gives you some sense of the discomforts involved in standard interpretations of standard interpretations are Copenhagen interpretations. Standard or Copenhagen interpretations of quantum theory. I'm going to close this mini lecture and have some coffee so I get less tongue-tied, and then we'll go deeper into standard interpretations by contrasting them with their competitors.